Hello, I'm Derek Hitchins. Systems engineering research, what is it? And really, what isn't systems engineering research? Let's start with what it isn't really. Strictly speaking, although the following are all important subjects and worthy of research in their own right, they're not really systems engineering per se. So we have engineering management, systems engineering management, program and project management, and lifecycle management. They are all management, organisation and business methods. So for the following, they're strictly not to be confused with systems engineering. So what is systems engineering? And even before that, what is a system? Well, a system's a dent in the fabric of entropy. It's a whole something complete. It's a whole comprising connected interacting parts, or it's an organised whole. So we may take systems engineering and transliterate it as organised whole creation. Ancient Egyptians did it. The Hymenoptera, the social insects, do it. That's the ants, the termites and the bees. And according to the song, even educated fleas do it. Here's a diagram showing the various second half of the 20th century, really, systems engineering projects, major milestones. There's a column at the left from 1940 going up to the top at 2020. You can see UK air defence on the left, high performance aircraft from the UK in the middle, finishing at the top with the Typhoon at the present time. On the right we can see the US with their Big Bang project systems engineering, going through Gemini, Apollo, Polaris, Aegis, Trident. And at the top, round about 1996, where there's a horizontal dashed line, you can see things starting to go a little pear-shaped, with Lord Robertson, the then minister, talking about defence procurement being done Japanese style, using COTS, commercial off-the-shelf, software and hardware, and the US Defence Acquisition Reform Programme. So both defence procurement in the UK and US defence acquisition are somewhat ailing, producing projects which are over time and over budget, or not producing projects at all. So summarising that diagram, first we had atomic, nuclear, and hopefully we're going to see fusion energy coming out. And we had NASA with Gemini, Apollo setting what we might call the gold standard in systems engineering. Then it's gone slightly pear-shaped because it's been defence dominated, with US defence acquisition particularly producing a parody of the previous systems engineering version. Really it was engineering management they were trying, and they called it systems engineering. Then there was non-defence emerging, air traffic management, emergency services, soft systems methodology, transport with air, road, and more recently rail and logistics. Japan, however, has taken a completely different route, and they've gone in for industrial lean volume production, taking on the US mass production system. And they've shown the West a more effective systems engineering operating at industry level, making automobiles, cameras, computers, white goods, brown goods. And it might reasonably be said that Japanese industry has set the platinum standard for systems engineering. It was founded and underpinned by system science, which views systems as wholes, comprised of interacting subsystems, also wholes. And that's comprised of interacting subsystems, also wholes. So we have hierarchies with levels, networks with extent, architectures as arrangements. Systems and subsystems were deliberately non-specific. They could be any or all of people, things, technology, processes, anything that performed functions really. And the strength of systems engineering lies in this abstract non-specificity. So systems engineering is not really like classic engineering. It's not to be confined to creating technical products. Nevertheless, there is a common thread to all systems engineering and to systems thinking. What is systems engineering essentially? Well, as we've seen, it's about creating organised wholes, so selecting the right subsystems, bringing them together in the right way, causing them to interact in the right way, orchestrating those interactions to create a unified whole, which performs with optimum effectiveness in its operational environment, so solving the problem that prompted its creation and, as it were, closing the loop. But what are the right subsystems and the right ways? That would be systems engineering research. So it's not really about what's in the subsystems, that's engineering. Instead, it emphasises the organisation, arrangement and interaction of all the subsystems at once to create a unified whole, which performs with optimum or best effectiveness in its operational environment. And as you can see, that is founded in three principles: synthesis, holism and organicism. Research agenda, always at the level of the whole in context. The architecture, performance, viability, availability, survivability, sustainability and support, always of the whole. Establishing, exploring, scoping the whole problem. Solving, resolving, dissolving the whole problem. To resolve is to find a solution that is good enough. To dissolve is to move the goalposts. Kobayashi Maru to those of you with Star Trek interests. Conceiving whole solutions, designing and proving whole system designs. Creating, evolving, enabling, fabricating, organising whole solution systems to match those system designs. Maintaining optimally effective performance and behaviour in operation. Disposal and replacement of the old by the new. All of those are research subjects. What constitutes a whole is a simple question, but may not be simple to answer. For continued performance in a changeable environment, a system may need to have mission management, resource management and viability management. The logic being that missions may be performed only if the mission system is viable and resourced. So the whole comprises mission, resource and viability management as a minimum. Behaviour management is important for higher level systems, particularly those with people in them. You can see here at the top, centre and bottom. At the top we have mission management, which works from an operational environment, collecting information, setting objectives, formulating a strategy and plan to achieve the objectives, executing the plan, cooperating with others, back into the operational environment. At the bottom we can see resources being acquired, stored, distributed, converted and disposal. And in the centre we can see the whole system being maintained viable, with synergy between all the parts, maintenance of the parts, so repair of anything that goes wrong, or replacement at least, maintenance, and there's evolution, survival and homeostasis or dynamic equilibrium of the whole. A slightly different view of what a whole is. Systems engineering, design, synthesis and realization. The overall systems engineering process appears to be one, first of synthesis of design, and then having designed the various things as a collection of interacting subsystems designs, then we realize or acquire the subsystems in the real world, put them together, and hopefully get in the real world the behaviour that we got from the system in design. The whole diagram looks a bit like that, which may look a bit complicated, but as you can see it goes from problem space at 1 through to solution space at 7. 2 is about developing concept solutions and concept of operations. 3 is about accumulating all the necessary functions to achieve the concepts and the purpose of the whole, including threat neutralization and taking advantage of opportunities. 4 is about the design synthesis, bringing all these various functional parts together into a composite design of the whole. And then 5 is about functional to physical mapping, specification of the whole parts interactions, and either developing and building or acquiring the parts and bringing them together such that you create the whole in the image of the design, and so the problem should be solved, resolved or dissolved and in the solution space. And this I refer to as being something like a systems engineering ontology. Hierarchies and networks, fairly obvious stuff, but people do have problems with it. In the center we can see a sibling system here. This darker one we shall say is our system of interest. We find that it exists interacting with other systems, its siblings, inside a containing system. And inside the system of interest we find a series of subsystems. If we look across in this direction, we see a horizontal section which is a network which has shape and form, so it has architecture. We see architecture at this level and architecture at this level. So a network view and a hierarchical view can be the same thing, they're just different ways of looking at the same thing. We have emergent properties at each of these levels. The levels in the hierarchy are effectively determined by emergence. Now, the system's architecture is of particular interest because we don't really know much about how to do it. If we consider on the left here we have an issue or problem situation, and here we have a robust architecture. We ought to know how to get from one to the other, and we really don't. There's a missing science here. We can put in architectural archetypes, we can put in mathematics, and we can learn from past and existing architectures, and we can use architectural metaphors to help us. Quite often we just use trial and error. There is a science missing. So what does architecture look like in basic terms? Well, it consists of, in simple system terms, of interacting parts. Here we can see 5 modules which are functionally tied together. So that's called a functionally bound block. There are 2 functionally bound blocks here, both of 5 parts, and they are loosely coupled by these 2 lines. If there's lots of lines connecting them up, then we talk about that being tightly coupled. This is clear architecture, this is somewhat confused architecture, and the tight coupling also brings with it the risk of oscillation and chaos. This is a channel tunnel architecture study that I undertook in 1988, I think, and you can see that the channel tunnel idea was to have a number of different departments. This is a printout from a computer, so these are abbreviations. Damage control, Interpol, activity sensors, environment sensors, customs, baggage inspection, safety control, and so on. Each of these items is represented by a letter on the diagonal of this n-squared chart. And the numbers represent interfaces with priorities between the various things. So there's a priority 3 interface between Interpol and customs. And there's another one here between logistics and operations. That's 6. And so on. We can cluster this n-squared chart using a genetic algorithm, and what we get out of it is a coherent pattern showing that we've got a functionally bound block, just like over here, at that level. And we have here another system at the center of an interface cross focused on K, which is operations, not surprisingly. K is a node in the system because it has interfaces with all of these other systems. So this has actually divided the whole thing up into a set of departments or functions which are concerned with what's going through the channel tunnel, whereas this one here is a set of functions and systems which are all concerned with the safety and repair of the channel tunnel system itself. So, more on the research agenda. We're interested in systems engineering paradigm and systems engineering methodology, methodology, which together ask the questions: what is systems engineering, and how do we do systems engineering? The SE paradigm being used in this presentation is simply that systems engineering is a problem-solving paradigm, and that it seeks to provide solutions, tangible solutions to complex problems and issues. The systems engineering methodology is then how do you go about solving problems and providing tangible solutions to them. The system type, scale, problem, solution and context are independent in both paradigm and methodology. However, they both lead to specific plans, methods and processes for specific problems and specific solutions in context. So we're interested in those processes, the methods and techniques. But is there an ideal systems engineering process? Is the ideal context dependent? Can it be proved ideal? How? What does ideal mean? And right back at the beginning, is there a single systems engineering methodology? Is it possible to have one methodology which tells you how to do systems engineering of all kinds? Here's a 5-layer model of systems engineering, starting at the bottom with product and subsystems engineering, which is about making artifacts, and to some that's the only real systems engineering. And many products can make a system. So at the next level we have project systems engineering, where lots of products are put together to make a system. And we have corporate wealth creation. Then many projects together make a business, and we have business systems engineering. And many businesses make an industry, so we have industry systems engineering. Japan works at this level. And then we have many industries can make a socio-economic system, so we have socio-economic systems engineering, which is about legal and political influences, government regulation and control. So there's a lot more to systems engineering than making products. And at each level and their interrelationships, we have another systems engineering research subject. Here's a view of industrial systems engineering, Japanese style. And we can see that we have a clockwise circle delivering goods to a market, and they come out of the market when they're obsolescent, scrap, recycled, resourced, and they go back in and round the circle. Products go clockwise. Market demand and money goes round anti-clockwise on the other hand. And what makes the whole rotate clockwise is continual innovation by the lead company, which is making people who are in the market with products believe that the product they have is somewhat old hat and out of date because there's a new one being produced by the company which has got more bells and whistles, more capability, works faster, has a hybrid whatever, and so we have to have one of those. And the item that we have at home, which is perfectly sound, is now out of date, so it's obsolescent. So the more innovation, the faster it rotates clockwise, and the more money rotates anti-clockwise. If we look inside business systems engineering, we can see that it's comprised of a number of project systems engineering put together into manufacturing systems engineering to form supply chain systems engineering. There may be things like IPTs, which does not mean integrated project team, but instead means integrated product team, a much, much simpler device. Then there's the subjects of complexity, emergence and chaos. Complexity, what is it? Is it good, bad, irrelevant, to be managed, or as some people believe, to be avoided like the plague? Systems engineering is believed to be about managing complexity in problem and solution, at least by some people. Emergence, is it inevitable outcome, or is it the result of bad engineering? And emergence comes also as counterintuitive behaviour and unexpected consequences, although both of those may say more about the observer than about the emergence. Can emergence be prescribed? Can it be created to order? And then there's chaos, which comes in at least two forms: deterministic chaos, or strong chaos, and self-organised criticality, or weak chaos. Is this again to be avoided at all costs, or is it inevitable, useful, and have the potential to be turned to advantage? Let's look first at complexity, said to be a composition of variety, connectivity, and convolution. Together they increase complexity, both perceived and real. systems engineering encapsulates complexity within organic subsystems. If the behaviour of a subsystem is known, its internal complexity need not be of concern to us at whole system level. And more complex may imply more functional capability, more adaptable, more resilient, more survivable, more innovation. But on the other hand, it might invoke greater defect rate support costs, longer design and development. So there's a major research interest in the value of complexity in man-made and natural systems. Natural non-linear systems have greater power densities, they are self-healing, they are auto-adaptive, and they self-replicate, which is something man-made systems aren't very good at yet. So can we learn how to apply and improve these natural techniques to improve our man-made systems? Emergent properties are properties of the whole not exclusively attributable to any of the constituent parts. It's a widely misunderstood term. If you combine commensurate forces, you get a resultant. If you cooperate between incommensurable systems, you get an emergent. There seem to be two sources of emergence going on at the same time, which is one of the reasons it appears to be so complicated. We'll have a look at what those are at the moment, but it appears to be occurring because of synergy between the subsystems and then synergistic reaction between the whole and other systems within the environment. A research goal would be to create properties to order, to create more bangs for buck, and to understand systems thinking, counterintuitive behaviour and unexpected consequences. Basically so we don't experience them, I guess. Emergence. A simple view is presented in the diagram here. We can see three levels, level -1, level 0 and level +1. At level 0 we have a containing system with other interacting systems in its operational environment. And the containing system acts and interacts and adapts to those other interacting systems. At the same time, at level -1, it has internal organic subsystems which are interacting with each other so as to produce a synergistic emergent behaviour. So we have emergence caused by the interactions between the organic subsystems, and we also have emergence caused by the interaction between the containing system and other interacting systems. So this is all going on and is observed then at level +1. A simple view, but it does give you some idea why it's a little bit difficult to understand and anticipate. Chaos. This is Lorenz's butterfly with the so-called strange attractor, which emerged when he started to produce dynamic simultaneous equations for the weather. Deterministic chaos is far from being random. It's quite well bounded. That line never repeats itself, but on the other hand it never goes outside those axes, and there are areas on that plane surface which it will never go into. So the climate is well structured and well confined. It's just not repeatable. And then on the right we have so-called weak chaos, exemplified here by Bakkenchen's self-organized criticality, which emerged when they tried to predict the behaviour of earthquakes and the onset of earthquakes by producing a model. It turned up that model, which was the weak chaos model, also provided sensible examples of the behaviour of stock price market fluctuations, the distances between motor cars on a busy motorway, deaths in war, so-called 1/f noise in conductors. In fact, as you look around the world, you see self-organized criticality almost everywhere you look, and it seems to be associated with constrained flows. It happens in manufacturing systems when you start to try and manufacture quite a lot. Instead of getting smooth flow from workstation to workstation, you start to build up queues, and then you put extra people on and get rid of the queue, and that turns out to give you a pattern of throughput rather like this one in the diagram. An example from ancient Egypt shows the relationship between deterministic chaos weather-wise at the top, which is causing good and poor inundations successively one after the other in ancient Egypt, and what happened to the population as a result. When there were good inundations, as the bottom line shows, we got an increase in population. However, it reached a point where the population was so large that it was eating all the food that was being produced, which was fine when there were good inundations and the population would increase, but when the poor inundations came along, there was too little food for the population and famine ensued, as shown by the stela on the right. So the population went up and down like a fiddler's elbow as the inundations went up and down according to the deterministic chaos, showing a rather interesting relationship between deterministic chaos, strong chaos, and weak chaos at the bottom. Auto-adaptive systems. This is a simple block diagram showing how one can look at a system and evaluate its properties, capabilities and behaviour as measured in the real world at the left. And then at the right you can use a simulation, an internal simulation, to work out what the design should be. And you can compare the design that is with the design that should be, and if the design that should be is in some way enhanced, and better able to adapt, you can reconfigure the design to reconfigure the real world system, and so adapt to the hostile operating environment. This is the sort of thing one would do if one has to leave a system on, say, the surface of a remote planet or asteroid, and you weren't at all sure what the environment was going to be. Behaviour management. Complex systems exhibit behaviour which is classically response to stimulus. Included in those complex systems would be socio-technical systems, the kind we make all the time. Human activity systems, so that would include systems engineering teams and teams of teams. Autonomous robotic systems, UAVs, automated patrol officers, servant systems, robotic soldiers perhaps, and the conception, design, organisation and realisation of such systems seems to involve some sort of behavioural psychology. A model of such behavioural management shows that, at least in humans, and it's the best model we've got, that's a relationship between nature and nurture. And you can see that we have a stimulus coming into an area called cognition, which is fed by our beliefs, world models of what's going on in the world, and tacit knowledge, such that we take the stimulus, which might be quite unknown to us, and we provide an interpretation of it based on what we know about the world and what we believe that stimulus might be. We then select an appropriate response from our experience and from our natural capability and from behavioural archetypes. We might decide this stimulus is something we have to do something about. We might be angered by it. We might create some sort of knee-jerk reaction to it. We then excite that and produce a response intent, which goes to other parts of the system, the physical parts, to create the response. If we look at our nature, according to Jung at least, that consisted of collective unconscious instincts, archetypes, libido, aggression, energy, character and emotion. Whereas this belief system is about beliefs, obviously, roles, stereotypes, categories, values, ethics, morals, ideologies, and particularly interesting, training. Our training gives us a belief system. And our belief system allows us to overcome some of our more crude natural behaviours. So we have belief system involved in choosing the behavioural archetypes. And here we have motivation to behave in a particular way, and motivation comes in two forms: achievement motivation and conformance motivation. So there you have a view of stimulus resulting in a response, and the response it results in is a function of nature, nurture, belief, world models and tacit knowledge. Complicated? Yes, it is. A simple block diagram of notional self-healing system with sensors, processors and effectors. And there's a built-in test system here with a system model telling the built-in test what should be available here, what should be observed. When it's not, it can deduce that one or other of these is ineffective, and it can be replaced, and the replaced item could be repaired using second line reserves here, and the faulty part returned to the stock of good parts ready for the next failure. So a continual self-healing capability. Bit simple, isn't it? Is it possible to maintain full service when there is a defect? And what about the connection issues and the power supplies when we take these things in and out? There's a lot more to it than that. Self-healing systems are important for items that are to be left alone in remote places where you can't access them to do repairs, or it would be expensive to. But it would be good if pretty well all of our systems were self-healing. Some research key indicators. If it doesn't advance the science, what's the point? And then there's synthesis, holism and organicism in several aspects for any kind, scale, nature and context. And we're interested in getting the right paradigm, methodology, strategy, processes, methods and tools. Synthesis and proof of designs as well as solutions. Performance, availability and survivability of whole solutions. Systems as being, doing and thinking, as well as form, function and behaviour. System mission, resource, viability and behaviour management. That gives us SMESH, synergy, maintenance, evolution, survivability and homeostasis or dynamic equilibrium. Then there's auto-adaptation, self-healing systems, autopoietic or self-organising systems, emergence, chaos, complexity, non-linear behaviour and non-linear capability, all of great interest to research. And final thoughts, or l'esprit d'escalier as the French would say. We've presented here a credible systems engineering research scope. It's exceptionally broad, showing the potential great power of systems engineering, yet not apparently identified with engineering and management. They are something else. They're layers on top of systems engineering proper. Is systems engineering really an engineering discipline? Is it conducted by multidisciplinary teams, or could it be conducted by an individual, depending on the problem and what was to be solved? Is systems engineering a discrete, distinct synthesis discipline? Does the systems architect engineer not so much be multidisciplinary as speak in many tongues, interpreting between engineering and many other disciplines? Is systems engineering more akin to detection, investigation, diagnosis, pathology and architecting? Or is that what good engineers do anyway? Thank you for listening.